Okay, let's jump right into example 3. No wasted time today. So we're doing optimization, right? How to systematically find optimal values, that is absolute maximums and or absolute minimums. Geometric problems are pretty good. Well, the calculus is replete with geometry problems. How about that? That's a good word, replete. So here's one example. A ladybug farmer has 500 inches, that's linear inches, of fencing, and wants to fence off a rectangular portion of a field that borders along a straight river to enclose his grazing ladybugs. Okay? So someone last year said, wouldn't this guy be a ladybug rancher technically? And I was like, shut up. He needs no fence along the river. Why? Ladybugs can't swim. I don't know if you knew that. Okay, that's like leaving a child in a car as a Class A misdemeanor. Might be new knowledge to you. Ladybugs can't swim. And I know you're saying, what about flying? He's clipped their wings. Ouch. That sounds cruel, but there's a proper way to do it. Okay, he's clipped their wings. So, what are the dimensions of the field, the rectangular field, that has the largest grazing areas for his hungry ladybugs? Okay? So he doesn't want to have to buy any more fencing. He wants to use all 500 of it, but he wants to make the area as big as possible. So this is one where we could draw a picture. So I'm going to go ahead and draw, there's the blue water, the water's over here, there's the river, and he's going to build a fence. Let's make the fence like this, like that. So it's really only 3 sides. So if he has 500 linear inches of fencing, assume, again, no waste. So he'll pin it down there, come up here, and just turn it on a right angle. So no wasted fence. You always assume no waste. So ideal conditions. I'm going to call this Y and I'm going to call this X. Okay, we used A and B yesterday. The variables don't matter, but they do vary. Okay, and we write the primary equation. We're trying to maximize the area. So what would be a letter for area? How about A? And in this geometric shape, what is the area of the rectangle? X times Y. Good. So right now, can't really use it because we have the area as a function of 2 variables, and we want it to be a function of 1 variable. So what's preventing us from making this rectangular pen infinitely large besides planet Earth? The fact that the guy wants to use what's on hand, 500 linear inches of fencing. So that's your constraint equation. If you want to label it, you don't have to. That's your main equation. And then your constraint equation is 500 has to equal, it's not quite the perimeter. What is it? 2y. Yeah, x plus 2y or 2y plus x. There's only one x that's needed because the river is the boundary on the other side. Okay. So once we have the constraint equation, remember we use that to help get our main equation in terms of 1 variable. We solve for the easier of the 2 variables, and we always consider what we're going to be doing when we plug it back in. So I would solve this one for x. So x is going to equal 500 minus 2y. This is a good time to maybe box that up just so you can find it a little more readily, because you may come back to that. But for now, we're going to use that to get this equation into 1 variable. So, comma, the area of the field is 500 minus 2y times y. And now we have it in terms of a single variable, where y is the perpendicular distance off the straight river. I will go ahead and distribute, and we get 500 minus 2y squared. And now it's time to consider at least a reasonable domain. It doesn't have to be perfect, okay? But what would be the smallest y could be? Yeah, 0. Now, if I let y equal 0, that means I'm just rolling out the fence along the riverbank. That's going to be like 0 area. It's not going to contain anything. So even though it would, yeah. You forgot to put the y on the 500. I sure did. I did not distribute. Man, that's going to be a big problem. Thank you. Yeah. Wow. Distribute 500y. I was hoping someone would catch that. All right, so 0 is not going to make sense. It minimizes the area. And so what's the biggest y could be? Well, y is going to be the biggest when x is the smallest. So if you let x equal 0, that would just be taking out the fence, coming straight off perpendicularly from the river, bending it in half and going straight back, which would be what? 250, right. Now, again, that upper bound is not super duper important. You could have called it 500 as well, and that would have been safe, okay? But you're coming straight out, bending it in half, and going straight back. That's also going to be 0, right? So somewhere between two zeros, you're going to have some optimal value. Now, also notice that the area equation is a parabola that opens downward. See that? And so now I know confidently, without having to justify, that I just want to find the y value of the vertex. And that will be not only the local max, but also the absolute max. So once we have the equation in terms of a single variable, and by the way, this is another equation to which you can return either one of these, because that gives you the area in terms of y. You don't have to box it, though. So now a prime or a prime of y is going to be 500 minus 4y. We set that equal to 0. We get 500 equals 4y. We divide through by 4, and we get 125. And then that's the final numeric answer, so I'll put units on it of inches. All right, so that's the only answer we got. It's going to be the one that we really are looking for. We know that in this case, too, because of what we already said. The parabola opens down. All right, so now that we have our optimal value, we can pretty much answer any question related to it. What did this one ask for? What are the dimensions of the field? All right, so we'll say, so the dimensions are, do we need to, again, keep the x and y associated with the values? Or can we just list it kind of like a 2x4? Or do we need to keep the x and y associated with it? Yeah, when in doubt, keep it associated. But in this case, it's very important because one of them is the perpendicular distance off the river and the other one is the parallel distance along the river. So the dimensions are y equals 125 inches by, and then how do I find x? I can plug that y back in there, and it's going to be 500 minus 125 times 2 is 250. 500 minus 250 is 250 inches. So we said that nature loves symmetry. We said the most optimal rectangle yesterday per length is a square. Does this pen or grazing area end up being a square? Yeah, it ends up being 2 squares. Yeah, that's a good way to look at it. So it's not a square. It's actually twice as wide. Oops, I didn't have x in front of there. By x equals, man, I'm not really 100% today. X equals 250. So it's twice as long along the river as it comes off the river. But yeah, if you bisected it in half, you would actually have 2 squares. So that's cool. And the reason it's not perfectly a square is because, again, we're not using the entire perimeter. We're using the river as part of it. So anyway, there you go. Had it asked for the actual area, you could have just taken that single y value that you found right here, and instead of finding the x and then multiplying them together, you could have just plugged it back into there or back into there. Okay? And this one didn't say to justify, so that's it. That's good. All right, so now the ladybug farmer can go out and lay his fencing and just be confident that he's done the best for his ladybugs, right? Yeah. Okay, questions on that one? That's pretty straightforward. All right, example 4. The same ladybug farmer from example 3. Y'all remember him? Yeah. He has purchased, this should be past tense, he has purchased some, get this, the World Wide Web is a dangerous place. He has purchased some expensive, extraordinary diva ladybugs, probably on the dark web, who require, get this is what makes them diva ladybugs. They require exactly 10,000 square inches of grazing in order to be at their optimal ladybug-like state, right? High maintenance. What is the least amount of fencing required now? He is going to go out and buy fencing. What is the least amount of fencing required to get these ladybugs at their optimal state if the farmer is still allowed to build along the straight river and not have a fence there? Don't think lady diva bugs can swim, and don't think that they still won't have their wings clipped. So, all right, so basically we're turning the tables here. We're doing it the other way around. We still have the straight river there. He's still going to be building a pen. But now what are we trying to optimize? Are we maximizing or minimizing now? Minimizing, right? We want to minimize, not maximize, the fencing. So if we use the same labels here, we'll call that y, we'll call that x. You always start with your primary equation. Let's call that f for fencing. Okay? And again, like we had before, it's going to be x plus 2y. But now instead of that being a constraint, that's our primary equation. So I need to get that in terms of a single variable. What is the constraint? Yeah, this is the disclaimer that comes when you buy these Diva Ladybugs. They require 10,000 square inches. So x times y equals 10,000. There's your constraint. So literally flipped from the previous question. All right, so now we can solve the constraint for either x or y just as easily. If you plug it back into your primary, though, you're going to have to double it if you solve for y. So I would probably solve for x. X equals 10,000 divided by y. And then you could box that in case you come back to it. So now we plug it back in over here. So the fencing is 1, 0, 0, 0, 0 all over y plus 2 times y. And this would be a good time again to get yourself a relevant domain. What is the smallest value y could be now? It's still the length off the river, so 0 is still the lower bound. But by my equation, can I actually let it equal 0? No. Okay, so that's we're not going to have to justify, so that's kind of the finer point. We wouldn't have to mess with it. And then what's the largest it could be? Well, that would be when x is its smallest, and I would need to then multiply it by something to get 10,000. So this is a safe upper bound, 10,000. We could probably do better than that, but it's not critical, right? We're basically just saying y can't be negative because it's a length, okay? So unless you're going to be using like the EVT, this is not super critical. Okay, so now we need to find, speaking of critical values, yeah? So f prime equals, can you take the derivative of 10,000 over y in your head? Bring the y to the top, it becomes to the negative first. And then you power rule it, so you get negative 10,000. Y to the negative second, which puts it back over y squared, plus 2. Now notice that is undefined when y is 0, but that's not even in our domain. We're only interested in the values that make it 0. So you can go ahead and set that equal to 0. Now again, the way you want to solve these is not by bringing the 2 across. Don't solve it algebraically. Do what we did in chapter 3. Get yourself a fully intact version of f prime. And then work on setting the numerator equal to 0. So I'm going to go ahead and multiply the 2 to get a common denominator by y squared over y squared. Okay, like that. And now f prime is going to equal 2y squared minus 10,000 all over y squared. I'll keep it equal to 0. Bless you. And what the heck, I'll just factor it out. F prime is equal to 2 times y squared minus half of 10,000, which is 5,000, all over y squared. Okay, so there's a fully intact factored version. We can still factor the numerator. It's a difference of squares, but not perfect squares. So I'll keep that equal to 0, and now that's going to be equal to 0 when y squared is equal to 5,000. That's implicitly setting the numerator equal to 0. You don't worry about the 2. And now when we take the square root, we consider always plus or minus. Does the negative one make sense, though? No. So you don't have to write it down, but at least you've considered it. It's going to be the square root of 5,000. Now let's see if this were like a multiple-choice question. Square root of 5,000 might not be the answer choice. So how can we simplify the square root of 5,000? Well, I know that 100 is a factor of 5,000, and it is a perfect square. And so that leaves me then 50, right? And then I know that 50 has a perfect square factor of 25. That's 25 times 2. So when in doubt, you can always get the prime factorization of a number, and then remember, pairs of numbers on the inside can become one representative on the outside. So it ends up being 10 times 5, that's 50 square root of 2. So that's a simplified answer, and that would be inches. Okay, now if you wanted to know if that's a minimum, and not a maximum, how can you tell? Well, let's think about the derivative. The derivative f prime, or the sign of the derivative, I should say, is determined by the sign of y squared minus 5,000. Would you agree? Because 2 out front is always positive and y squared is always positive. So if you just think of the graph of y squared, let's call it y. No, let's just say y squared minus 5,000. That graph is going to look like this. It's going to have a y-intercept of negative 5,000, and then it's going to come up like that, and then it's going to intersect right there at 50 square root of 2. Remember, our relevant domain was from 0 up to some upper bound, which really didn't matter. Okay, so we're not seeing the other part of this parabola on that side. That's going to change signs again. So if you had to justify, notice, the part of the derivative that contributes to the sign, it goes from a negative to a positive. Now, if you just say that part goes from negative to positive at that point, that's a local argument, right? And that would make it a local what? A local min. But here's where it becomes a global. That piece of the derivative that contributes to the sign is negative everywhere between 0 and 50 square root of 2, which is our relevant domain, and that part of the derivative that contributes to the sign is positive everywhere to the right of 50 to square root of 2 up to our value of 10,000. And therefore, that value not only is a local min, but it minimizes absolutely the fencing. Okay, so there's the amount. So that's just the y value. So we have our optimal value in our possession. Now we answer the question, what is the least amount of fencing required? Okay, so to figure out the least amount of fencing, we need to come back over here and plug it into our effing equation, our fencing equation. Okay, so let's do that. So 10,000 all over 50 square root of 2 plus 2 times 50 square root of 2 inches of fencing is required, or at least that much is required. And if we wanted to get the dimensions of the pen, we could certainly do that too. We already have the y value. You can plug it back in up here to get the x value. All right, so you can simplify that if you want. I don't think I'm going to. Or maybe, I'm not going to. Okay. So there you go. It's flipped around. Now, I've seen another version of this type of problem where you're trying to minimize the cost. And here's what it would look like. Building perpendicular to the river might cost like $5 per, we'll just keep it in terms of inches, whereas building parallel to the river might only cost $3 per inch. And you want to minimize the cost. So then what you would do is just say 2y, that's the length of y, times 5, plus 3 times x. That's your cost equation. And then you'll have some constraint, and you could go that route. So a lot of different variations on these building these fences or whatever type problems. Okay? And there's a lot of different scenarios where one of the sides doesn't have to be built upon. I think there's a couple of tests out there where you have like there's a house like this that's built, and you want to build a fence, that's just right here. And what are the optimal dimensions or something like that? Or you want to build it out to here, and you want it to extend a certain distance off the house, but you don't need a fence along the other. So there are all kinds of ways where you can kind of set up your equation, but the idea is the same. Okay, primary equation for what it is you're trying to optimize. Look at your constraint equation. If you have 2 variables or 3 variables, you need to get it in terms of 2. Solve for one, plug into the other, simplify, find the domain, take the derivative, set it equal to 0, and then answer the question. Okay? Comments or questions on that? Okay, so notice that in this case, the endpoints were not really relevant because they collapse the geometric structure down to 0. And that's the case for most of those types of problems. But there are instances where the endpoints are relevant, where they could possibly be the solution. So let's look at example 5. Find the point on the curve of y equals x squared closest to the point 3, 0. How do you know this is optimization? Closest to, right? So we're trying to maximize closeness. How do you maximize closeness? Minimize distance. There you go. So we're trying to minimize the distance. So here's one where a picture could help, but it's not a geometric picture. It's just the graph of x squared. Let's go ahead and draw that, the graph of x squared. That looks something like this. I'll label it. I want to find the point on that red graph now that's closest to the point 3, 0, which would be right here. All right, so just kind of look and see what you think might work. If I go straight across to the vertex, that distance is what? I already know that distance to be 3. If I went straight up perpendicularly here, I already know that distance too. What is that distance? 9. Okay, so I already got the fact that it can't be the one up there, but maybe it's the vertex. Now, would it have a shot at being closest way over here on this part of the graph? No. As soon as I go to the left of the vertex, I know it's going to be greater than 3. So I don't even have to go over there. Similarly, is it worth looking at any point that's to the right of 3? No, because that's going to be greater than 9. So I've kind of created some endpoints here that are relevant, right? That would be from x equals 0 to x equals 3. I know that the closest point has to be somewhere on that interval from x equals 0 to x equals 3, or that would also be from y equals 0 to y equals 9, depending on whether we get it in terms of x or y. Now, can we just assume the closest distance is 3 at the vertex? No, because guess what? It might actually be somewhere on the interior. So I'm going to draw this line to here, and I don't know what that distance is, but I'll call it big D. And what is the coordinate of this point? Well, you can call it either x comma y, or you can actually call it x comma x squared if you want. I'm going to call it x comma y. All right, so it might be somewhere in there. So here's what we need to do. If we're trying to then minimize the distance, I need to come up with a formula for the distance formula, big D, between the arbitrary point xy and the fixed point 3, 0. Do y'all remember the distance formula? Yeah, x sub 2 minus x sub 1. Yeah, squared. There you go. So I'll do it like that. It's the change in x squared plus the change in y squared. Those are your two short sides of your right triangle. And then you're trying to find the hypotenuse, so then you add them together, take the square root of it. All right, so for us, that's going to be the square root of, I'll do x minus 3 squared plus y minus 0 squared. There's your primary equation. I'll simplify that real quick. That's the square root of x minus 3 squared plus y squared. All right, so that's not a bad primary equation, but now I have the distance in terms of both x and y. And I want it to be in terms of either x or y. So what is our constraint here? What is preventing us from going right up there in the face of 3, 0 and saying, here I am, close enough for you? The function, right? I have to stay on the parabola. So the equation, y equals x squared, the equation on the parabola is the constraint. It's given to you. In fact, if you would have called this point here not xy, but x comma x squared, you would already have your distance formula in terms of a single variable. But in this case, we didn't, so now we'll just plug in. So the distance is the square root of x minus 3 squared plus y squared, which is x squared squared, or x to the 4th. And now I could put a comma since it's in terms of one variable, and I know that x has to be between 0 and 3. And in this case, those endpoints are relevant. In fact, the vertex, when x is 0, may in fact be the closest point. That could very likely be. So this is not a geometric structure now. where the extremes of the endpoint of the interval collapse it down to nothing. Okay, so now I just need to see if I can find any critical values between 0 and 3, right? So let's find the derivative, d prime. Well, that's the whole thing to the 1/2 power. So by the chain rule, that's 1/2 times the whole thing to the negative 1/2 power. So that's just x minus 3 squared plus x to the 4th times the chain rule, the derivative of the radicand. All right, and the radicand is going to be 2 times x minus 3 to the 1st times 1 plus 4x cubed. Now let's clean that up. D prime is going to end up being, if I distribute this in the red piece, I get 2x minus 6, and then plus 4x cubed. And in the bottom, I'll have a 2 times the square root of the quantity x minus 3 squared plus x to the 4th. Now remember what I said. We're only interested in the critical values that make the derivative what? Undefined or 0? 0. Where did then the values that cause 0, which are the numerator, where did those values come from? They came from the chain rule when I took the derivative of the radicand. So here's kind of another interesting thing, and this could be a strategy. If you're trying to minimize the radical, making it as small as possible, you could actually just minimize the radicand. In other words, you can go off to the side and say let r for radicand equal that, and just take the derivative of that. And then you'll just end up with this piece. It's not much more work to just consider the whole thing and then realize that the bottom piece, which comes from the radical, is really out of the question anyway. But some people like to do that. So anyway, I'm going to do one more thing before I set the numerator equal to 0. I can divide out a 2 all the way across. So I can get x minus 3 plus 2x cubed, and then all over the square root of x minus 3 squared plus x to the 4th. And now when I set that equal to 0, I can now set the numerator equal to 0. X minus 3 plus 2x cubed equals 0. And now we will solve that after lunch. Mm-hmm.